All right, let's jump into a deep dive on circles. It seems like you've been doing some pretty in-depth exploring with geometry lately. We've got your notes here, and wow, it's a lot. I mean, you've got everything here, from like the basic definition of a circle all the way to some pretty complex equations.
Yeah, it's always really cool to see someone like really digging into the nitty-gritty of circles. You know, they seem so simple at first glance, but there's a whole lot more to them geometrically than meets the eye.
For sure.
Yeah.
So let's start with that basic definition that you have right here at the top of the stack. A circle is a set of all points in a plane that are the same distance, called the radius, from a fixed point, which we call the center.
Right. A great way to think about it is like a perfectly round fence enclosing a specific area.
Exactly.
And you know what else you've highlighted in your notes? The whole concept of a locus of points, which is such a fundamental idea in geometry.
Right, the locus.
It's like a set of all the points that meet a specific condition.
Yeah.
In the case of a circle, the condition is that all those points got to be a certain distance away from that center point.
Makes sense. So it's not just like individual points, but like a whole bunch of points that all have to follow the same rule.
Precisely. And you know what's even cooler? This whole idea of a locus, you see it everywhere. I mean, think about it.
Yeah.
The planets orbiting the sun, each one follows a specific path, right?
Right.
It's all based on their distance from the sun and the sun's gravity. Or even something as simple as like you drop a pebble in a pond. That ripple that spreads out.
Yeah.
That's a locus of points, all the same distance from where the pebble hit the water.
I never thought about it like that.
Yeah.
So it's like the circle is kind of this fundamental building block for all these patterns we see around us.
Exactly. And then you get into equations, and that's where things get really interesting. You've got that standard equation of a circle written down here, xh2 plus yk2 equals r2.
Yeah, I got to be honest with you. Equations can be kind of intimidating sometimes. Like, can we break this down for the listeners who maybe haven't thought about math in a while?
Totally. I mean, picture this. You've got a dartboard. The center of that board, that's our HK, point in the equation, and then the radius R. That's like the distance from the bullseye to the outer ring.
Okay, I see that. And then, so how does the actual equation work, like in terms of that dartboard?
So let's say you throw a dart. That dart lands somewhere on the board, right? It's got an X and a Y coordinate, like a map location.
Okay.
You take those coordinates, you plug them into the equation. If everything works out perfectly, boom, that dart landed right on the circle.
It's on a circle.
If not, well, it landed somewhere else on the board, maybe inside the circle, maybe outside.
Oh, so it's like a way to pinpoint if that point is on the circle or not.
Exactly. You've even got some special cases of this equation in your notes. Like, what if the circle is centered right at the origin of our coordinate plane?
Right at the center.
That's when HK becomes 0, 0. So the equation gets a whole lot simpler. By 2 plus y2 equals r2. Nice and clean.
Definitely. And I see you've even explored cases where the circle like touches the X or Y axis. Does that change things?
Absolutely. Let's say the circle just grazes the X axis. That means the radius R is the same as the Y coordinate of the center K. So the equation becomes xh2 plus yk2 equals k2. We can really simplify things depending on how the circle sits on the axis.
Oh, I see. So it's all about like adjusting the equation based on the circle's position.
Exactly. Now, you've also included this more general form of the circle equation. By 2 plus y2 plus 2gx plus 2y plus c. Looks a little more complex, right?
It does, yeah. A little intimidating, if I'm being honest.
Oh, it might look scarier, but it's actually super powerful. Notice those g, f, and c terms. And they're constants, but they're like little clues telling us about the circle. We can actually use them to figure out where the center of the circle is. It'll be at the point GF.
Interesting. So even though it looks different, we can still find the center of the circle using this equation.
Exactly. It's like a little mathematical detective game, you know?
Yeah.
We can also use this equation to figure out the radius.
Oh, really? How do we do that?
Well, the radius is going to be the square root of G2 plus F2C. It's a bit of a formula, but it lets us calculate the radius directly from the equation.
Okay, so by understanding these equations, we're basically gaining a deeper understanding of the circle itself.
Precisely, and it goes even deeper than that. Your notes mention something about real, point, and imaginary circles. Ever heard of those?
Yeah, I have. But honestly, I've always been a little confused by the idea of an imaginary circle. Like, how can a circle not be real?
It's a really cool concept. It all comes down to the value we get when we calculate the radius using that formula we just talked about, the square root of G2 plus F2C. If we get a positive value, then we're good. That means we have a normal, real circle with an actual radius.
Okay, makes sense.
But if that value turns out to be 0,
Yeah.
that means the radius is 0. Basically, the circle collapses into a single point. We call that a point circle.
Oh, okay, so it's like the circle just shrunk down to its center point.
Exactly. And then there's the imaginary circle. This happens when the value under the square root ends up being negative.
Okay.
Now, we can't take the square root of a negative number and get a real answer, right? That means the radius is imaginary. It doesn't have a real measurable length.
Whoa, so it's like a circle that only exists in the world of math, not in the real world.
Exactly. It's a concept that really pushes the boundaries of how we think about geometry.
That is mind-blowing. I'm starting to see just how deep the rabbit hole goes with circles.
And we've only just scratched the surface. But let's switch gears for a second. I see you've also been looking into how points relate to circles.
Yeah, that's something that I've always been kind of curious about. Like, how do we know if a point lies inside the circle, outside the circle, or right on the circle itself?
That's a great question. And guess what? We can use the Sokol's equation to figure it out. Remember that dartboard analogy?
Yeah.
So you throw a dart, it lands somewhere on the board.
Okay.
We can use the equation to see if it landed inside the scoring area, inside the circle, outside the scoring area, outside the circle, or right on the edge on the circle.
Okay, so it's like the equation acts as a referee. It tells us if the point is in, out, or right on the line.
Exactly. You just take the x and y values of your point, that's your dart's location, and you plug them into the standard equation of the circle. Then you compare the result to the square of the radius, r2.
I see.
If the result is less than r2, your dart's inside the circle, equal to r2, right on the edge. Greater than r2, it's outside.
That's really neat.
Isn't it? And speaking of points and circles, your notes also mention something called the power of a point. Ever given that much thought?
I have. And I have to admit, it sounds a bit mysterious. What does it even mean for a point to have power over a circle?
All right, get ready for this, because this is where things get pretty fascinating. Think of it like this. Any point that's outside a circle, it's got a certain influence on that circle. We call that influence the power of a point. And it's a numerical value. We can actually measure it.
Okay, I'm intrigued. How do we measure this power or this influence?
It all has to do with tangents and seconds, those lines that interact with our circle. Let's start with tangents. You draw a tangent from that point to the circle. The power of the point, it's equal to the square of the length of that tangent line.
So if a point is farther away from the circle, the tangent line would be longer. Does that mean it has more power?
Exactly. It's like the point is kind of exerting a force on the circle, and the farther away it is, the stronger that force is.
That's a really cool way to think about it. But what about the seconds? You mentioned those too.
Right, seconds. Those are the lines that cut right through the circle. They intersect the circle at 2 points. We can use those to calculate the power of a point too, but the formula is a little different. It involves the distances from the point to those 2 intersection points on the circle.
Okay, so whether we use tangents or seconds, we're basically figuring out how much that point outside the circle can affect it.
You got it. The power of a point is this powerful tool we use in geometry to understand relationships within circles. And you'd be surprised how many different ways it comes in handy.
I'm already seeing that this deep dive is going to be full of surprises.
Oh, yeah, you haven't seen anything yet.
I can't wait to see what other fascinating things we can discover about circles.
It really is amazing, like, how much depth there is when you really start digging into these seemingly simple concepts. And speaking of digging deeper, you've got a whole section here in your notes about tangents going into a lot more detail.
Yeah, tangents. It seems like they're everywhere in these notes. I always think about them like, those perfectly placed ramps you see in like skateboarding videos, just grazing the edge of the curve.
I love that analogy. It's perfect. A tangent line intersects the circle at just one point, right? Just like that skateboarder smoothly transitioning from the ramp onto the curve. And mathematically, we can define a tangent by looking at the perpendicular distance from the center of the circle to that line. And if that distance equals the radius of the circle, boom, you've got a tangent.
So it's like, it's got to be just the right distance away from the center to just barely touch it.
Exactly.
Without actually going through it. And I see you've even written down like equations for finding the equation of a tangent, both in general and for specific points on the circle.
Right. Those equations are like essential tools. If you're working with tangents, they let you figure out precisely like what that line is that's just grazing the circle in that very specific way. It's like having a blueprint for building that perfect skateboarding ramp.
It's pretty amazing how we can take these like geometric ideas
Mm.
and translate them into algebra, into equation.
Really?
It's like we've got this secret code that can unlock all the secrets of the circle.
I love it. That's a great way to put it. Speaking of secret codes, you've also got some notes about the chord of contact. Have you spent much time thinking about that one?
Yeah, I've been trying to wrap my head around it, but I'm still a little fuzzy on it. What is this mysterious chord?
All right, so picture this. You've got a point outside the circle, right? And you draw two tangents from that point to the circle.
Okay, yeah.
The chord of contact is the line segment that connects the points where those two tangents touch the circle.
Oh, okay. So it's like a bridge formed by the circle itself, connecting those 2 points where the tangents touch.
That's a perfect way to think about it.
And I'm guessing there's an equation for finding that chord too,
No,
right?
you bet. And you can actually derive it using the coordinates of that external point and the equation of the circle itself.
Wow, this is really making me see how all of these like different geometric concepts are connected.
Oh, yeah, it's all related.
They all like build on each other. It's
Ah.
like this really intricate web of relationships within the circle.
Oh. And what about normals? I see you have some notes on those too. Are those related to tangents in some way?
They are. Normals are lines that are perpendicular to the tangent, right at the point where the tangent touches the circle.
So it's like if the tangent is that gentle ramp, the normal is like dropping in vertically on that ramp.
Exactly.
It makes sense.
And just like with tangents, you can find the equation of a normal too. You just use the coordinates of the point of contact and the slope of the tangent.
Okay.
It's all about understanding how these lines and circles relate to each other. Speaking of relationships, you also have some notes about something called a director circle. I got to be honest, that name sounds a bit intimidating.
Oh, don't let the name scare you away. It's actually, it's a really cool concept. Remember when we talked about perpendicular tangents earlier?
Yeah.
Well, the director circle is all about the points where two perpendicular tangents to the original circle intersect.
Oh, okay.
So it's the set of all those points, all those perfect intersections where you can get that 90-degree angle.
So it's like a circle that's made up of all those perfectly balanced tangent intersections.
Exactly. And guess what? It has its own equation too. If you have a circle with the equation by 2 plus y2 equals a2, the director circle is going to have the equation by 2 plus y2 equals 2a2.
No, that's interesting. So the radius of the director circle is connected to the radius of the original circle.
It is. The radius of the director circle is the square root of 2 times the radius of the original circle. And here's another fun fact. The director circle is always concentric with the original circle, so they share the same center point.
Oh, I see.
Pretty neat, huh?
This deep dive is really making me appreciate all the different things you can do with circles.
Oh, there's so much.
It's amazing. Okay, before we move on, I do want to touch on another concept that you have in your notes here. Pole and polar. Now, I've always found this one to be a bit tricky, so buckle up. Okay, I'm ready for it. I've seen those terms in your notes, but I have no idea what they actually mean.
Okay. So imagine you have a point, right? It's outside the circle.
Okay, yeah,
You draw two tangents from that point to the circle.
right.
Now you connect the points where those tangents touch the circle, that line. That's the polar of that original point. And that original point, we call that the pole.
So it's like every point outside the circle has this special line associated with it that's determined by those tangents?
Exactly. And it goes both ways. You give me any line outside the circle, I can find its corresponding pole. It's like this partnership between points and lines, and it all revolves around the circle.
And like they have this like secret handshake.
I love that. And here's where it gets really cool. Remember when we talked about the chord of contact?
Yeah, the bridge formed by the tangents.
Right. Well, a chord of contact is actually the polar of the point where those tangents are coming from.
Whoa, it all connects. It's like we're uncovering these hidden pathways within the circle.
Exactly.
And I see you also have something in your notes here about families of circles. Now, what in the world does that mean? Like, are these circles getting together for like a family reunion or something?
You could think of it that way. So basically, circles can be grouped into families based on shared characteristics, kind of like human families, right? So, for example, all the circles that pass through the intersection points of two other circles, that's a family. Or all the circles that are tangent to a specific line at a certain point, that's another family. Each of these families, they have a special equation that kind of captures what makes them unique.
So it's like we're finding these common threads that tie these circles together.
Exactly. It's all about recognizing those patterns and relationships, even in something as seemingly simple as a circle.
This is blowing my mind.
Yeah.
I'm really starting to see that circles are way more than just simple shapes.
Oh, absolutely.
There's this whole like world of math and geometry that they can unlock.
There is. And we're about to go even deeper into that world as we explore how circles actually interact with each other. You ready for that?
Oh yeah, lead the way. I'm ready to see what else we can discover. Okay, so let's dive into those circle interactions. You mentioned common tangents before, right?
Yes, common tangents. These are lines that are tangent to two or more circles, like bridges connecting those circular islands.
Oh, I like that visual. So these tangents are kind of like reaching out to connect with other circles.
Exactly.
And you mentioned there are like two types of common tangents, direct and transverse. What's the difference there?
All right, so imagine you've got two circles side by side, right? Direct common tangents, they cross between the circles, like a bridge going straight from one island to another. Transverse common tangents, they don't cross. They kind of run alongside the circles, keeping them separate, almost like parallel paths.
Okay, so direct, they connect, and transverse, they separate. Makes sense. But how do we know if two circles will have direct tangents, transverse tangents, or maybe even no common tangents at all?
Ah, great question. It all comes down to the relationship between the radii of those circles and the distance between their centers. So let's say the distance between the centers is bigger than the sum of the radii. That means the circles are far enough apart to have four common tangents, two direct and two transverse. But if the distance between the centers is exactly equal to the sum of the radii, then the circles are just touching each other. They're externally tangents, and we only get three common tangents.
So it really is like a dance between the circles, you know.
It is.
Their sizes, their positions, it all affects how they connect or don't connect.
Exactly. And there are even more cases we can explore, like what happens when the circles overlap or when one circle is completely inside the other. Each scenario gives us a different arrangement of common tangents.
It's incredible how much complexity there is,
I know.
just from two circles and a line.
Right. And speaking of complexity, you also have some notes about the angle of intersection between two circles. Have you been giving that one some thought?
Yeah, I have, but I'm not sure I'm totally clear on it yet. Is it just the angle like where the two circles cross each other?
You're on the right track. The angle of intersection is the angle formed between the tangent lines that we draw to each circle at their point of intersection. It's like a measure of how sharply or how gently those two circles are crossing each other.
Oh, okay. So if the circles just barely touch, that angle would be pretty small, right?
Exactly. The angle would get closer and closer to zero as the circles get closer to just touching. And on the flip side, if they cross at a really steep angle, the angle of intersection would be much larger.
Makes sense. And you also mentioned a special case, orthogonal circles, right? What makes them so special?
Yes. Orthogonal circles are super cool. They intersect at right angles, so they're tangent lines at the point of intersection. They're perpendicular to each other.
Oh, so they're like meeting at a perfect crossroads.
Exactly. And there are all sorts of interesting geometric properties that come into play when you have orthogonal circles.
I bet. So much to explore there. Okay, last concept I see in your notes here. It's the radical axis and radical center. Now, those sound pretty intense. Can you break those down for me?
I know, the names sound a bit intimidating, but the concepts are really elegant. Remember our discussion about the power of a point?
Yeah, the point's influence on the circle.
Right. Well, the radical axis of two circles is the set of all points, where the power of a point is the same with respect to both circles. It's like this line of equilibrium where the influence of both circles is perfectly balanced.
So it's a dividing line between the two circles. That's pretty neat. And what about the radical center? Where does that fit in?
The radical center is where the radical axes of three circles meet. It's like the balancing point for all three circles.
Oh.
And here's a cool thing. The radical center is also the center of a circle that's orthogonal to all three of our original circles.
Whoa, it all comes back to orthogonality. It's like everything with circles is connected somehow.
It really is. And,
Yeah.
understanding these concepts, it opens up a whole new way of looking at and analyzing relationships between circles. And these aren't just theoretical ideas. They have real-world applications in fields like engineering and physics.
This deep dive has been amazing. I've learned so much about circles, from their basic definition to these like mind-bending concepts like the radical axis and all these different types of circles.
I'm so glad to hear that. It's been great exploring all of this with you.
It really has. I can't wait to see what other shapes and patterns we can unravel together.
Yeah.
Until next time.